Hello, lovely children. Sorry for the hiatus, but I am back. On this video, I would like to request that you do not like the video too quickly. I think it's starting to short circuit the YouTube server, so just do that at a slower pace this time. Today we're doing complex number basics. Yes, we should know most of all of this. Maybe not the last little bit today, but this is just going to get it back in your head. So when you see IB questions, you at least have this little refresher real fast. So let's talk about what a complex number is. Remember, a complex number is just a number that has an imaginary part. So technically, though, So complex numbers, when written as a set, is usually written like that, like a funny C with a line. You know how like integers are written like this funny Z. So complex numbers are written as that C. So something that's important that I want to make sure kids understand is if this is the set of real numbers, the set of real numbers is inside the set of complex numbers. All real numbers are complex numbers. So that's an important thing that you know before we get started. Because, so like in rectangular form, that's the first thing. That's what we're most familiar with. That is a complex number. We usually write complex numbers as Z. Rectangular form is written as A plus BI. So we have a real part plus an imaginary part. So back to what I was saying before, all real numbers are complex numbers. So like just the number 1 is a complex number where the imaginary component is 0. Hopefully that makes sense. But yeah, so remember we learned this previously, that we have this complex plane where we have a real axis and an imaginary axis. So let's say I have like Z1 equals 1 minus 2i, and Z2 equals, I don't know, 3 minus 4i. Oh, let's do it. Sorry, that was dumb. Let's do a different quadrant. Negative 3 plus 4i. Okay, so big thing that you have to remember. So even though the math that we're going to do for this is very similar to vectors, complex numbers are numbers, so they are points when graphed in the complex plane. So Z1 would be 1 in the real direction and 2 down in the imaginary direction. So there is Z1, the point. And then Z2 would be negative 3 in the real direction, 4 in the imaginary direction. Whoops. Whatever. Z2. Okay. So remember this word, modulus. Modulus, it gets compared to magnitude for vectors because the math is the same. And it really is. It's just Pythagorean theorem. It just means distance away from this origin. So we calculate that, obviously, using Pythagorean theorem, like doing the real direction squared plus the imaginary direction squared and square root. So we'll do one real fast. So like the magnitude of Z2, sorry, I said the wrong word, see? The modulus of Z2 is written with these bars like this. That would be, obviously, the square root of 3 squared plus 4 squared, which we've done 100 times. It's 5. So that means the distance Z2 away is from the origin is 5 units. Okay, you should be good with that. Now, argument, so that doesn't have like a special symbol usually besides maybe just theta. It just means the angle. So argument, or sometimes it's written like this, just arg of something. So we'll do argument of Z1. So Z1 is here. So we want the angle. It's just like trig. You've done this 100 times. You know, we want the angle made from the positive x-axis. So we do that doing inverse tan of the b value over the a value. So like if this was in the real plane, it'd be y over x, but like the y value is kind of like is the imaginary value, so b. So let's see, when we do that, we'll do this in degrees. So if I do inverse tan of -2 divided by 1, I get -63.4. So remember, you have to ask yourself, because inverse tan is bounded by values between the first and fourth quadrant, you have to ask yourself, is that angle that the calculator told me my answer, or do I need to add 180 to write the appropriate angle? In this case, I'm already in the fourth quadrant, so -63.4 is the correct angle. If we wanted to write that as a positive angle, we would just add 360 to that. So 296.6. And that's the argument. It's just the angle. But you've been doing that with me for 2 years now, so I think you got it. All right, so powers of I. You remember this. Powers of I, we know, is the square root of -1. So I squared, logically, squaring that square root just makes this -1. I cubed is the same thing as I times I squared, so that therefore becomes -I. And then I to the fourth is just I squared, which would just be 1. Now, we usually don't write, I was just writing that so you know what we're talking about. But I to the first, we just leave as I. We don't usually write the square root of -1. So remember, we'll just do one of these. You've done this many times with me. If I did like, what is I to the 57th? Because you know that like I to the 5th would be 1 times I. So it's like back in this pattern. So this pattern is going to repeat for every 4 powers of I. So you're really just looking at this number and dividing by 4 and thinking, well, what is the remainder? Well, the nearest number divisible by 4 would be 56. So that means 57 divided by 1 has a remainder of 1. So this is really the same thing as just I to the first. So I. Okay. I have a feeling you're fine with that. Let's remember how to multiply. So if it was like 2 plus 3i -1, I don't know, plus 4i, who cares? You multiply the same way you multiply binomials, it's just distributing, so it would be -2 plus 8i minus 3i plus 12i squared. So 8i and -3i is 5i. And then we have to remember I squared is -1. So really 12i squared is -12. So this just gets written as -14 plus 5i. And then if we were to take the same complex numbers but divide them, we don't really like having imaginary parts in a denominator when we're dealing with rectangular form. So what we do is we multiply by the conjugate. So remember, if z is equal to a plus bi, the conjugate in an IB, conjugate is denoted by z like asterisk. That is a minus bi. A doesn't change, but you change the sign of b. So we multiply both the numerator and the denominator by the conjugate. So then you just do all that distributing again. But the whole point is that the denominator, when you multiply a complex number by its conjugate, it's always going to turn into a squared plus b squared. The reason is you can kind of see, like -1 times 4, -4i would be positive 4i, and then 4i times -1 would be -4i. The I values are always going to cancel when you do this distributing. So a squared plus b squared for that is going to be 17. The top we did earlier. No, we didn't do that earlier. I should have done it differently. That would have saved time. Oh well. So let's do it again. So -2 minus 8i minus 12i minus 12i squared. So all we got left to do is combine terms. So that's equal to, so -12i squared is the same thing as positive 12. So that would be 10. And then minus 20i over 17. And it's a good habit. When we write complex numbers, you're not done until you've split it into imaginary parts and real parts. So we would write this as 10/17 minus 20/17 I. So that's how we divide. Cool. Again, you've seen this before. All right, last thing today, conjugate root theorem. You can kind of remember this from when we did, or you have done, the quadratic formula. So like, you've done the quadratic formula before where you have a imaginary part. And the conjugate root theorem, I don't know if we've ever said it out loud before, but it makes sense when you think about the quadratic formula. So the conjugate root theorem says, if a polynomial has a root of a plus bi, so if it has a complex root, it has to also have another complex root of the original root's conjugate, so a minus bi. That was kind of, sorry, that got cut off at the worst part. Conjugate of a minus bi. Because think about it, like say, like going back to algebra 1 when you were first doing quadratic formula, like you would simplify down and you'd get to like -2 plus or minus the square root of, I don't know, 3i all over, I don't know, 21, who cares? So it has this plus or minus in it. That's what causes that conjugation. I don't think I need to explain that much further. I think you get it. Okay, so let's make up a problem. Let's say, let's find a quadratic behave. Okay, you don't want to behave. Okay, moving on. With root, I don't know, 1 minus 2i. That's an I, believe it or not. 1 minus 2i. Okay. So, if it has a root of 1 minus 2i, remember, if it had a root of like 2, you would write a root of like x minus 2. But if it's a root of this complex number, it doesn't change anything. So it becomes x minus 1 minus 2i. And conjugate root theorem states, if that's a root, then so is its conjugate. Now, if we multiply this all out, we will get a quadratic without any imaginary components. So let's do that. So we have x squared, then let's do x times, so minus 1 plus 2i times x, and then minus 1 minus 2i times x, and then plus 1 minus 2i, 1 plus 2i. Ooh, gotta hurry. Okay, so this is x squared minus x minus 2ix minus x plus 2ix. And this is 1, like all that's going to cancel, leaving 1 minus 4i squared. So that spits out x squared minus 2x plus 5, if you simplify that. Okay, I have 2 seconds left. Thank you. Love you. Goodbye.